Okay, we're going to now specialize our work a little bit and consider the case of constant acceleration motion. We will find out in Chapter 4 that this corresponds to the forces that are acting on an object being all constant. That will give constant acceleration. So this is an important special case, but it's not always true. We've been looking at a lot of examples where the acceleration is not constant, especially in those graphical examples. But you got to remember this is a specialized assumption. So we're going to make the assumption, which is written right here. If the acceleration x component, again we're imagining something's moving on the x-axis, in the time period we're concerned with, so from t equals 0 to some later time t, is constant, then there are three consequences of that, and those consequences come from some calculations, and if you're not someone who's had calculus, you don't need to worry about it. In fact, no one in physics 110 needs to worry about it. It's a rather elementary in terms of integration to get from the assumption ax equals constant to the following three equations. But for us, they're just going to be kind of given to us in physics 110. First equation is that the, well, it looks like this. I've got the items labeled here. So the idea is I've specified some time t equals 0 and some later time t between which the acceleration, x acceleration is constant. And what this means is the velocity, this Vx represents the velocity at that later time t, and the Vx0, the 0 is supposed to represent t equals 0, represents the initial velocity, or the velocity at time t equals 0. And Ax represents that constant acceleration. In many problems we'll know what Ax is, and t is how long it takes to get from t equals 0 to that later time t. Okay, so that follows from, I'm not claiming we showed how to do it here, but using some calculus, you can get that equation from the assumption Ax equals constant. So Ax is independent of time. Second equation that follows is x equals x0 plus vx0t plus 1/2 axt squared. Again, what do those symbols mean? And we'll be doing a lot of practicing with this. The x represents the x-coordinate of the object at that later time t. x0 represents the initial position, or x at time t equals 0. Vx0 represents the same thing that it did before, the initial x velocity, and Ax is the constant acceleration that's valid for that time. T is how long, of course, it takes to get from t equals 0 to t. Finally, this third equation isn't really independent of these first two equations. You can get these two directly using calculus, and then what you could do is solve this first equation for t equals, and then plug it into all the t's that are in this equation, and solve for Vx squared. And what we find is that Vx squared equals Vx0 squared plus 2ax times x minus x0. The meanings are the same as the things we said before. Vx is the final x velocity, that's the x velocity at time t. Vx0 is the initial x velocity, and x minus x0, sometimes you'll see me write this as delta x. It is the displacement at time from t equals 0 to the later time t. Okay? Let's just think about what these mean in terms of functions of time. We've been talking about graphs of x versus t and vx versus t and ax versus t. The assumption that ax is constant between t equals 0 and that later time t means that ax is a constant function of time. So if I plotted ax versus t, we'll see examples of this, it would just be a flat line, you know, with a value that equals the constant value of acceleration. Whereas v as a function of t, I guess in high school maybe you're used to graphing things as a function of x, but that t is playing the same role as maybe the x if you like graphing functions as a function of x. So this is like y equals mx plus b. This is a linear function of the variable you're plotting on the horizontal axis, which for us is t. So that's telling us that vx is going to be a linear function of time. So ax is a constant function of time. Vx will be linear. It's like the equation for a line. And similarly, this is telling us if we plot x versus t, x is on the vertical axis and t is our horizontal one. And again, normally we would think of the horizontal one as being x in an elementary math class, but just the names have changed here. When you have, you know, a constant times x squared plus a constant times x plus a constant, that's the equation for a parabola or a quadratic function of time. So this is saying if we plot x versus t, we would expect to get a parabola. So let's just look at some particular graphs that are associated with these. Here we could imagine, again, if x is a quadratic function of time, a parabola, here's, for a certain period of time, this kind of looks like it would be a parabola, right? It's a piece of a parabola that's valid for a certain period of time. And if we use our skills for going from position to velocity, remember that the slope of the tangent line to the position versus time graph should give us the velocity versus time graph. So here, the slope of the tangent line at 0 looks like it's 0, right? At time t equals 0, the slope of the tangent line kind of looks like it would be flat. That's a slope of 0. Slope of the tangent line is 0 up here means the height of this function should be 0. Slope of the tangent line becomes a little bit positive, even more positive. That means the height of this function becomes a little bit positive, more positive, and even more positive. So that makes sense. And notice that, I'm talking about this qualitatively, but it looks like the velocity being a linear function of time, which we asserted up here, is consistent with the position being a quadratic function of time. So that seems reasonable. And again, we said the relationship between velocity and acceleration versus time graphs is the slope of the tangent line up here is equal to the height of the graph down here. So slope of the tangent line, if we have a linear function, is the same everywhere. If we attach a tangent line, we're going to get the same slope. It's a constant positive slope of the tangent line, and that means the height of this function should be constant, just like the slope of the tangent line is constant up here. So that seems consistent. So that's one set of graphs that illustrates these three properties that I have written in red. Here's another one. This is a different quadratic position function as a function of time. It's like an upside down parabola. So this would represent something that's going in the plus x direction really quickly to begin with, right? It has a very large positive slope of the tangent line. Then it slows down in the positive x direction. Its slope of the tangent line gets smaller and smaller. Slope of the tangent line goes to 0. So it's going very quickly in plus x. It slows down and momentarily comes to rest at this time. And then the slope of the tangent line starts to become negative. So it starts going in the negative x direction. It has a negative velocity. Okay? So the slope of the tangent line is very positive, less positive, 0, slightly negative, more negative. The height of this graph is very positive, less positive, 0, slightly negative, more negative. So that seems consistent with it, and even though we're just talking qualitatively, it seems like this linear graph that we've shown down here would be consistent with this quadratic graph. And if you know some calculus, the derivative of a quadratic function is a linear function, maybe that makes sense to you, but we don't need to know that in Physics 110. And again, the slope of the tangent line of this graph equals the height of this graph. Slope of the tangent line is constant and negative all the way down the graph. That means the height of the acceleration versus time is constant and negative. That's what we're seeing there. That's another example. Now, I said up here that x is a quadratic function of time. That's almost always true, except in the case where ax equals 0. If ax equals 0, that certainly is a case where ax is constant. It might just be constant at 0. If ax is 0, this quadratic term goes to 0, and then x becomes a linear function of time. So these equations are also consistent with that. So the position might be a linear function of time. That means the acceleration is actually constant at 0. Slope of the tangent line is constant and negative. Height of this graph is constant and negative. Slope of the tangent line of this graph is 0, 0, 0. Height of this graph down here is 0, 0, 0. So we see graphs of this type are associated with 0 acceleration, acceleration being constant at 0. Again, these three equations are only valid for in between 0, t equals 0, and a later time t, if the acceleration has a constant value. That constant value could be 0 or positive or negative, but you got to make sure that it's constant in order to apply them. Okay, and they tell us what if the acceleration is constant, it tells me what Vx, if I know what Vx is at the initial time, it tells me what Vx is at a later time. I just plug in that time, as long as the acceleration is constant. If I know what x is at the initial time, and I know what Vx is at the initial time, it will tell me what x is at the later time. You just plug in the t you want. All right, so we're going to practice actually getting some useful information out of these, what sometimes people call them kinematics equations. They're constant acceleration kinematics equations. And we're going to need to practice, being very clear in our thinking about defining what t equals 0 and the later time mean, which way the axes point. So here's just a couple things that you should keep in mind and being very definite about when you're using the constant acceleration kinematics equations. Your problem is going to be defined in terms of some physical situation, and there are no real axes sitting around in the world. So we need to define, in terms of the problem, which way are we thinking of we're going to treat as plus x, and where is the origin? Okay, so where am I going to call x equals 0, and which way is the positive x direction? Because otherwise we don't even know what the x-axis means to apply these. Similarly, we have to define what the initial time is when t equals 0 and what the final time is. So in a particular problem, you've got to say, when this happened, that's t equals 0. When this other thing happened, that defines what the later time is. And of course, I've got to check that ax is constant in between both of those. If it's not constant, if it ever changes, even just once, you're not justified in applying the kinematics equation. And then finally, we need to look at these three kinematics equations and choose an equation, hopefully, that involves some symbols that we know. There's a lot of symbols in here. We're going to have to get used to this. We want it to involve symbols that we know and the symbol for what we want to know in the problem. So if there's something that we don't know and we don't want to know it, we'd prefer to just avoid that equation and use another one if possible. So here's an example problem that we'll do together. Golfer puts her ball straight toward the hole. The ball's initial speed is 2.52 meters per second, and it decelerates at 0.65 meters per second squared until it comes to rest. I should have said, or it falls into the hole. So it's either going to come to rest before it reaches the hole, or maybe it would have come to rest after it passed the hole, but it falls in the hole in the meantime. The question we want to answer is, will the ball make it to the hole, which is 4.8 meters away from the hit point? Okay, so this problem, I won't always really ask you to line things up so much, but since this is our first problem practicing with the kinematics equation, we want to be very explicit and lay things out in a systematic manner. If the direction from the putt to the hole is plus x, notice I've done some of the defining for you. Normally, you're going to have to define that for yourself. So we're going to call the direction the ball is moving plus x. That seems to make sense. What are the initial x velocity and x acceleration? That means what x value is it at time t equals 0, and what velocity does it have at t equals 0, and what acceleration does it have at t equals 0? Notice I didn't say where the origin is, but it kind of makes sense to maybe take x equals 0 at the hit point, just to simplify things, right? It starts out at x equals 0. We want to know what the final x is where it comes to rest and find out if that is before or after it reaches the hole. So let's make some careful definitions here. I'm going to imagine that at x equals 0, that's the hit point. Again, I didn't say that up there, but that seems a reasonable thing to do to make things simple. We hit it at x equals 0. That defines what t equals 0 is. And the later time t, that final time t, is where the ball stops rolling. And what we're going to just kind of ignore where the hole is. Where it stops rolling might have been before it reached the hole at 4.8 meters. It might have also been after it reached the hole. And if it's after it reaches the hole, we would know it falls in the hole and it made it. The important thing for us is that it has constant deceleration in this period until it comes to rest. So we're just going to pretend the hole isn't there and find out how far it rolls before coming to rest. And that rest point is going to define the later time t. Okay, so it certainly has constant acceleration. That sort of lines up the variables. Now we want to ask ourselves, what is the initial x velocity and x acceleration? And we've got to be very careful to use our axis there. Since initially it's going in the plus x direction, the x velocity is going to be positive. But since it's slowing down in the positive direction, that corresponds to a negative x acceleration. So if I put those two in there, the initial x velocity in my chosen coordinate system is positive 2.52. That's just this value that's given there. It's positive because it's going in the plus x direction. But when something is slowing down in the plus x direction, that corresponds to a negative ax. And so the 0.65, which is just the magnitude of the acceleration, has to come in with a minus sign. If I had chosen a different axis direction, I might not have had the minus sign, but for this one I've chosen, those are the initial x velocity and x acceleration. Those are important because they're going to come into any three of these equations we use, so we always need to know those unless they're one of the things we're looking for. All right, second question. The ball probably doesn't go exactly 4.8 meters. How far would it go? I cut off part of the problem here, but I said if the hole were not there, how far would it go? And if the answer is it would have gone less than 4.8 meters before it comes to rest, then we would say it doesn't make it to the hole. If it would have gone more than 4.8 meters before it comes to rest, it would have made it to the hole. Okay? Now we need to look at what is being asked and choose an equation from these three that hopefully involves what we know. Here are some things we know and what we want to know. Now the important thing for what's being asked here is we want to know how far it goes. In other words, we want to know if we call x initial equals 0, then x final, or x final is going to be defined by when it comes to rest. And so I want to know what that x final is. If x equals 0 is when it's hit, then if x final is when it comes to rest, that x final is the variable I want to solve for. So I don't know anything about the time it takes to come to rest, and I also don't want to know anything, apparently in this problem, about the time it takes to come to rest. So I'd really like to avoid these first two equations if I possibly can, for the way this problem is phrased. They'll be different for other problems. You might have been asked, how long does it take to come to rest or hit the hole? And we might be interested in the time. But here we're asked, how far would it go? We don't know anything about how long it takes to come to rest, and we don't want to know. So I'm going to hope that using this third equation, let's just write it down and see if we know everything except what we want to know. I really want to know that delta x. That's the displacement between the hit point and the point at which it comes to rest. And if it's less than or greater than 4.8, we'll be able to make a decision. So how far does it go? Let's write down that equation and let's try to plug in what we know. We already know what Vx0 is. We know what Ax is. We want to solve for delta x. And for our definition, where the final point is when the balls come to rest, that means the final Vx, the Vx at that later time t, would be 0, right? By definition, our final is when it comes to rest. So I'm going to plug in 0 here and the other two numbers. It's very important to keep those minus signs in there. It crucially hinges on having all the right signs here. And notice the only unknown is delta x in this equation. So I can put those numbers in, put this one on the other side with a minus sign, and then divide by this negative number once I multiply them out to solve for delta x. And I get delta x is 4.88 meters. So to answer the question, does it make it, if the hole weren't there, it would have gone 4.88 meters before coming to rest. Does the ball make it to the hole 4.8 meters away? Yes, it does, because it would have fallen in the hole before it came to rest. All right, that's our first example, and we're going to do another example shortly.